Hi, folks. Welcome to chapter number 10. First lecture. I hope I'll be able to complete what I want to convey in this lecture alone. This is about high voltage laboratories, importance of high voltage laboratories, layout, certain precautions, certain clearances, certain uh, how they are laid down, etc. High voltage laboratories. Yeah, we'll be talking about application of high voltage laboratories, testing equipment, basic laboratory guidelines for basic guidelines for setting up a high voltage laboratory. If you want to set up a high voltage laboratory, you must carefully listen to this lecture uh, on what are the high voltage laboratories around the world. And there are some experimental setup. I mean, experiments set by me for the students to conduct individually. We will not be talking much about it. Uh, that because that depends upon the facilities available in a high voltage laboratory. Although many of the facilities can be made with just small efforts, I would say. So, yeah, you must read the top paragraph. For the development of technologies in scientific subjects, fundamental knowledge and concepts are evolved through continuous academic efforts supported by dedicated research work over decades, in some cases even over centuries. It is the Technical University of Dresden, which has got a history of high voltage engineering department to the order of almost 2 centuries, and and wonderful lab exists even today, and the labs have continuously research work, experimental work has been going on there, which has uh, evolved the concepts, the what I have tried to convey. The concepts in high voltage engineering, what I have tried to convey in all my lectures, especially the concept of three kinds of fields, is unique and developed in Dresden, in the high voltage engineering department of Technical University of Dresden. And that is the approach for investigating, for assessing the performance of all the dielectrics. So, high voltage laboratories play a very, very important role if we want to establish work, academic work. I mean, that would a laboratory gives not only the education but also adds to research and to some extent nearby testing work of the product developed nearby in this field can come to the laboratory for testing also. So all the three purposes of high voltage laboratories are fulfilled if you have a proper high voltage lab in your institution. Laboratories are not only an essential requirement for any scientific development, but they are also an integral part of the institutions for, you can say, assets of the institutions, which the investment in the laboratory pays back over the time. And Yeah, let me first of all show you the laboratory in the next figure. These are the two photographs as you see it here. On the top, this is the laboratory which I set in IIT Kanpur. I took time to set it gradually and with the minimum possible investment. The laboratory on the top, you can see it is equipped with, uh, as I mentioned, for the measurement of partial breakdown. You need the setup to be partial breakdown free, and for that we have a 200 kV partial breakdown free AC power frequency test transformer. Then that is at the back. As you see, we have shown you some photographs. We'll show it again. Then um, in the forefront, the foremost front, this is a 400 kV high voltage DC generator, and at the on the left side at the back is the 500 kV impulse generator. So it is equipped with AC power frequency, with DC, as well as impulse generator. And the ratings, as I told you, 200 kV AC, 400 kV DC, and 500 kV impulse voltage. And all these are high voltages cater to the need of any kind of experimental work required for up to 66 kV rated voltage. For 66 kV rated voltage comes now today as part of the distribution network of power. Transmission is at higher voltages. So for the all distribution network rated voltages, it can take care, the laboratory can take care. In the center of the laboratory, as you see, where the mat is, that is the area where we put our test object for applying the high voltage. This laboratory has got not very large area, and some of the experimental work uh, require much larger area, especially when you want to conduct, for example, some work under the rain. So you can't produce rain artificially, or certainly you won't get the natural radia inside uh, within this laboratory. So there is a, as you see on the right side, on the top, there is a wall bushing installed. As here, I'll mark it here. This is the wall bushing installed. So all the voltages generated inside the laboratory can be taken out just adjacent to the laboratory premises. There is an open area available, which is serving as a open air laboratory premises. So with the help of this wall bushing, all the it has been wall bushing has been installed, which can withstand all the maximum voltages what I described, AC, DC, and power frequency, which can be taken out. And in the figure B at the bottom, you see the wall bushing coming out into the open area. So the problem of limited space for experimental setup or where you want to apply the high voltage is resolved with the help of this wall bushing, and all the voltages generated inside are can be taken out to the open air bay. In the open air bay, as you see it here, the two insulator strings on the left side, They are actually at the moment uh, stretching a 25 kV traction catenary. Traction, the electric traction 25 kV catenary has been stretched in the open air, and the investigations for the clearance to the ground from the high voltage uh, conductors of the traction are being investigated with this experimental setup. And the best part in this laboratory is that we have also conducted experimental work with natural rain, with natural fog conditions, because it is in the open air. You don't. We have conducted with artificial rains also, but besides, we could conduct the experimental work. Maybe coming there at odd hours, when because the fog would be there early morning. Sometimes there is rain at odd hours, so we have to rush and perform the experimental investigations on this catenary for determining the optimum clearance required with the ground. So this is an advantage of this kind of a setup, which has been able to cover with minimum of, let me tell you, investment. I would see the teachers, if they are listening to this these lectures, they are most welcome to contact and learn how to set up a high voltage laboratory, a good high voltage laboratory with the minimum of expenditure. Another thing I wanted to mention here, sometimes you have to uh, take an insulator string or some insulated support for taking the high voltage generated by the equipment to the test object. So that for that we have put here, as you can see here, this this is a an insulator string made out of toughened glass. Toughened glass insulator string is hanging from the ceiling, and below there it helps to to lay temporarily the conductor for uh, taking the voltage to the test object. And this is one of the test object shown here in this laboratory. Hmm? Yeah, if you uh, will come to how do uh, other laboratories look like too. Let me show you first, when I'm talking about this very laboratory, I'll show you one slide. Yeah, this is the uh, experimental setup I have already shown in the perhaps in the last lecture, and also in the slide uh, at the back. This is the experimental setup at the back here. This setup is shown here. Uh, yeah, so this was the first 100 kV PB free, partial breakdown free test transformer, power frequency AC test transformer. And I've described why these big domes and etc. are needed to be connected. And this was the first PB free 100 kV test transformer, mm, which came up something like more than 35 years back in our country, in India, by Kirloskars in Bangalore. And this was installed in the laboratory, with which has an insulated container, fiberglass reinforced container in the middle. As you see, this is the insulated container. So to make it PV free design, it was not metallic, instead insulated container was needed. And on the right side is the 1.1 nanofarad coupling capacitor. 1.1 nanofarad coupling capacitor, uh, and these are the connected. And the whole setup is PV free. The whole setup is PV free. So we'll come to it, the PV measurement. Then when you have very large laboratories, large in the sense which can produce very high voltages, it becomes uh, a liability if you plan very high voltage laboratories in indoors, because the cost of the building alone goes so high that it may be to the tune of the equipment what you are wanting to install. And it is not advisable to have very high voltage generating laboratories indoors. Rather, they are outdoor laboratories. So what you see here on the left, A, now by this time you should be able to make it out what kind of a high voltage generator it is. It is nothing but a DC high voltage generator of rating 1200 kV. In A, it is 1200 kV DC generator. Indoors in our laboratories, yeah, this was the one in the forefront, as I mentioned. This is the one here. This on the in the forefront, 400 kV DC generator. And what you see here, outdoors, this is 1200 kV DC generator with a current rating of 200 milliamperes. This is the one, 200 milliampere A. 1200 plus minus 1200. Ours is also plus minus 400 kV. Obviously, it may ours cannot give you plus minus 400 kV at a single time because of the clearances required, but this can give you plus minus 400 kV. So that becomes 2400 kV DC generator. Plus minus 1200 is 2400 kV DC generator having a current rating of only 200 milliamperes. As we have discussed, that the requirement of current from the generator, DC generator, is very, very small because there is no charging current required by the capacitance formed by the dielectric. Only some amount of losses like polarization, etc., the current is required, which is very small, 200 milliamperes only. And on the right, B, you must have also been able to recognize. I have shown you in the previous lectures. This is nothing but 1600 kV, 6 amperes, a very high amperage rating for AC high voltage test, high test voltage generator. And that is in 16 kV, 1600 kV, sorry, 1600 kV AC test generator. So as you can see here, this appears to be in 2 stages. 800 each has been designed, if I'm not mistaken. Yeah, in 2 stages. The 800 each is giving you 1600 kV AC power frequency, 6 ampere. 6 ampere is when it can test objects requiring very high magnitude of current. There will be power cables and transformers, as you know. And 1600 kV is good enough for any research work for 1200 kV rated voltage. For 1200 kV rated voltage, the test voltage generated of the order of 1600 kV is good enough for any developmental research work if you go for 1200 kV transmission voltage. And uh, and the third one is your 5 MV. C, as you can read it here, 5 MV, 500 kilojoule, 25 stages. That means in each stage is generating 200 kV, an outdoor impulse generator, which is housed inside here. To protect it from the adverse weather conditions, it has been housed in a closed uh, chamber, you can say. And this is the high voltage electrode on the top, segmented disc electrodes. In here also, this is nothing but segmented disc electrode are being used as high voltage electrode. On the left is the actual impulse generator, 25 stages housed inside the tall enclosed chamber. And on the right hand side, you should be able to make it out by now, is nothing but the RC divider for the measurement of high voltage. Resistance and capacitance divider. For such high voltage measurement, a capacitive divider, pure capacitive divider would be very expensive. So this is a resistive and capacitive divider. The same thing here, this appears to be a capacitive divider. For AC power frequency, you need a capacitive divider. And for DC measurement, you need a resistive divider. So the resistive divider appears to be somewhere in the last stage, if I'm not mistaken. This is the where the resistive voltage divider is installed. So each high voltage generating equipment would also have a high voltage measurement system. As we have learned, sphere gaps are no more used for the measurement of high voltage. Dividers are used, and in all these three also we have the dividers, suitable dividers, what we have also discussed. You would be, you might have already read, you'll be glad to know that this high voltage laboratory in the open air belongs to CPRI, Central Power Research Institute, Hyderabad. And this is one of the foremost and one of the laboratories in our country which is having highest test voltages, and it can cater to the need of development, research, and testing work for the level of 1200 kV transmission voltage. At present in our country, the highest transmission voltage is 800 kV. AC power frequency is 800 kV. DC is plus minus 800. So this can generate plus minus 1200. So it can take care of the highest AC and DC transmission voltages, and even the envisaged maybe some after 3-4 decades the AC power frequency transmission voltage may be needed to the level of 1200 kV. Today it is 800 kV. The next, if India goes for still higher, in the next coming few decades, it will be 1200 kV. At present, 1200 kV is not required. Total installed capacity of our power generation can be met for transmitting that installed capacity of power can be met very easily with 800 kV at present. We have also discussed in the world highest is 1150 kV in Russia, and there are not many other transmission lines at that level. So over the world, 800 kV in practice is the one of the most widely used transmission level of voltage. So this is, as you can see, the size of all these equipment is such that all these equipment you could not put indoors, as I have put in my lab in IIT Kanpur. The ratings are so less that it can be put in a not very big laboratory. So as you generate higher and higher voltages, the size of the equipment increases. Not only the size of the equipment, you have to have a certain clearance required by such high voltages. Yeah, and for the clearance, the space requirement increases tremendously. We'll discuss what is the clearance requirement. So it is advisable to have such high voltage laboratories in open air. And then there is no depth of space for experimental investigation and the mm, for the experimental research work. All is fair, but the equipment must be designed in such a way that it can withstand, it can bear the impact of bad weather. In Hyderabad, rain would always be there, and the heat, the high temperature, and high rain conditions would be there. Yeah, in Europe, such equipment are also installed outside, which have to take care of the still worse conditions when it snows. I mean, the equipment has to remain intact even under the heavy snow conditions. So, in our country, that problem is not, at least in the flatland areas. Snow is not there, and but rain is there, and the whole equipment should bear the heavy rain conditions. They are always tested with heavy rain to be able to withstand. So I hope you have got an idea about the uh, size of the equipment and size of the laboratory required. So the next we can go for major high voltage uh, test equipment. We have discussed the requirement. These are the test equipment required. Uh, you can say, uh, yeah, uh, a special requirement is AC power frequency test set. A special requirement is that of PD or PB free equipment. That is what I have also explained it to you already. This equipment in our lab is PB free. Obviously, when we go for still very high voltage, as we discussed this now, 1200 kV DC and 1600 kV AC, it's very difficult to uh, mm, make the equipment to be absolutely PD free. There may be some magnitude of partial breakdown going on in the equipment. To take care, you can see the toroid rings here. These are called toroid rings. This is also toroid rings, and here these are the toroid rings. Connectivity is made with such large dimensional tubes. This is also a tube electrode of very high uh, diameter, you can say. It's all to increase the size of the conductor, the radius of the conductor to the extent possible, in order to bring down the electric field density around it. That is one of the ways of stress control. So that makes the size of the equipment further. And in this case also, pipes, dome are taken to make the whole setup PB free, but this is only up to 100 kV. To achieve PB free up to 1600 kV may be very difficult. So, but partial breakdown measurements are performed not at such high level of voltages to the order of 1600 kV. So there would be some partial breakdown activity in the very high voltage test generators, as I showed you in the previous slides. Okay, and this setup is free, PB free till up to 95 kV. It has been verified. And we can perform the partial breakdown measurements. We have learned in the previous chapter the partial breakdown measurements. Yeah. Yeah, we have discussed this high voltage DC test generator, high voltage impulse generator. The one I showed you is 500 megawatt, megavolt. Sorry, 5 megawatt. This was 5 megawatt, 25 kV impulse generator. And the highest in the world, I have also mentioned earlier, in the highest in the world is 7.2 megawatt. 7.2 megawatt, highest in the world. That 7 to may have 24 stages also if each one is having 300 kV, and if each one is having 200 kV, the 36 stages may be required. There is a possibility to go for single stage up to 300 kV. So this is how the impulse voltage generators in the high voltage laboratories appear to be. Now let's talk about the layout of the laboratories. Yeah. Yeah. The laboratories that cater to the needs of very high rated voltages of the order of 800 kV and above, as we talked, are therefore established indoors, as their requirement of space is extremely large. Sorry, I said indoors, are established outdoors because of the large requirement of the space. And the in a high voltage laboratory, the equipment needs to be handled is so bulky that often the big indoor high voltage laboratories have a built-in crane. When we talk about the indoor, they may not have such high voltages as I showed you, but lesser high voltages. For example, I have shown you a high voltage generator to the tune of that was I have shown you to the tune of 1800 kV. No, 6 by 6, 1200 kV AC frequency. I have shown you, which is indoor, which is there in TU Dresden, which I have shown you earlier in the lectures when we were talking about the generation of high AC test voltages. So what happens in I've come across very large indoor high voltage laboratories also, and these laboratories have to handle such heavy weight equipment, even the test objects, etc., that those indoor laboratories, big indoor laboratories, may have may or do require a crane all throughout their length from one end to the other, a crane moving or supported at the wall, and that crane is used for taking a big equipment or big part of the equipment from one place to the other place within the laboratory. Such high voltage laboratories are are made. We do have the biggest high voltage laboratory in our country are at two places. One ISC Bangalore and another one at BHEL Bhopal. They are two of very big size indoor laboratories. So if you have a chance, you should be able to visit there. And yeah, have a crane system. Then these laboratories, uh, yeah, the height of such, not only the width and length, but also the height of such laboratories is required is also very, very high, because some of the test equipment, especially the impulse generator, may have a very tall height. So, height of the laboratory, indoor laboratory, is also very large, and these high such for such heights, you would like, uh, if you want to have some audience, or if you want to yourself while performing the experimental work in the laboratories in at some place, they may be at the first level. I mean, suppose they are of the order of three-story building. So at the first level and at the second level, around when the building is there, you may have balconies opening in the laboratory, where people, where from people can observe the phenomenon going on. So the provision of balconies in the height of the walls is there in some laboratories. Then other provisions, I'll tell you, which I've come across in the laboratories, are that uh, the entry points of the laboratories, the doors and the main gate, their shape, their size must be planned in such a way so that the bulky equipment is able to reach inside. If you make the openings to be very small, it would not. How can you take the bulky equipment inside? Then, uh, uh, yeah, uh, yeah. Uh, then another provision you must make. Yeah, I did not mention all high voltage laboratories, indoor, I'm talking about, need a provision that you can make complete darkness inside the lab. Why do you need complete darkness inside the lab? When you perform some experimental work, and suppose you are trying to observe the corona activity deliberately or by default. I mean, you may produce corona by the experimental setup to investigate the corona, or when you are performing experimental work on some objects where undesirable partial breakdown is taking place in air, that is also corona, then you should be able to make it out where it is taking place. But such corona activity cannot be seen in the broad daylight. So you must darken the laboratory. So to be able to visual partial breakdown activity anywhere in the setup or in the experimental setup, experimental gadget, it is going on, we should be able to see. So darkening the laboratory is one of the requirement for when you set a high voltage laboratory. Then besides darkening, uh, the another very important thing when you set up a laboratory, where should be the control room for various equipment. You got to have one control room where from you can control all the equipment. I mean, control all the equipment. That means you energize the equipment and change the magnitude of the voltage and perform the test from one place. For there won't be a separate control system installed at different places in the laboratory. There has to be one control room, and the positioning or the situation of the control room should be such that you can have a bird's eye view on the equipment. You can see the equipment. There are no obstructions on the way when you are sitting in the control room to any of the uh, high voltage generating equipment. So darkening situation of the control room, for audience balconies. Then another important thing, you must make fencing all around in the laboratory between the two equipment, and for the people to move from one place to other in the laboratory, the fencing has to be done. And the fencing, when an equipment is energized, the fencing must display that the equipment is energized. And if by any mistake someone opens the door, the uh, equipment must be de-energized by if somebody, because when the within the fence of energized yeah, equipment for generating high voltage, within the fence no human being should be allowed to enter. When the this is true in even in any high voltage lab, even in a small high voltage lab, fencing has to be done to protect or to safeguard the human being inside the premises where high voltage experiment is going on. So these are some layout requirements. Yeah. Now let's talk about clearance requirement for safety. This is also a very, very, I mean, how far, uh, or you can say how near a human being can go, how near a grounded object can be placed, or ground should be from the high voltage test equipment. So that is clearance, and that is required for not only human safety, that is also required for the equipment safety. It should be, the placing of the equipment should be optimized in such a way that uh, it doesn't require any extra floor area. These are all constraint, very severe constraint for setting up a high voltage laboratory indoors. So it should, you have to take care about every inch of the floor area available to you. So the clearance, one must work out what is the requirement of clearance to the grounded object from the high test voltage generator equipment. Hmm? Uh, Let me see. Uh, Yeah, so total floor area requirement will be determined by the clearance. And uh, and once you set up the equipment, the clearance, you've taken care, the equipment is not moved. All these equipment, for example, the AC, power frequency, DC, impulse voltage generators are so big that once you place them, these are not movable. These are fixed at their places. And this is and you must fix them, you must place them at the safe distance, that is the clearance distance, which is safe. Then, yeah, let's go to the next slide. Yeah, so uh, uh, some guidelines for clearance people have been working the to optimize the safety distance for clearance uh, anywhere. Let it be in the laboratory, let it be in the substation, let it be in electric traction. The safe distance of clearance with the grounded object is a very wide uh, subject, and people have been experimenting, trying to optimize the safe clearance distance. Even now, it has, because the clearance requirement for different equipment and different weather conditions, etc., may be different. So that clearance requirement people have been working since very long time. Uh, as you can see, this is a clearance requirement. This graph by IEC 60060. So this is the clearance in meters given here, clearance in meters, and this is the test voltage in peak. Test voltage, yeah. Clearance, for clearance, you would always need uh, to consider the peak uh, magnitude of the voltage. That comes basically for AC power frequency. For DC, it is always the peak. For impulse voltages, it is only the peak which is under consideration. So for test voltages, K in kV peak, this has been recommended. This graph has been recommended by IUC. The recommended minimum clearance of uh, uh, extraneous live or earth objects, live or, I mean, clearance not only with the grounded objects, with other energized objects also, it comes into picture. I mean, there are two equipment, and suppose both of them are working at the same time. So what should be the clearance? So the clearance not only with the grounded objects but also live objects to the energized electrode of a test object during an AC or positive switching impulse. Why AC power frequency and positive switching impulse have been taken into consideration here? Because at the uh, they have some similar characteristic. If you measure breakdown of a, let's say, air gap for the two uh, by applying AC power frequency and positive polarity switching, the breakdown strength of the gap would be minimum and almost equal by when you measure with these two types of voltages. For other types of voltages, the DC, other negative polarities, impulse, other lightning impulse, negative polarity, even negative polarity switching, the breakdown strength will be higher. For negative polarity, the breakdown strength is always higher. For DC, it is higher. So the breakdown strength of air, that is what is the concern here, because the clearance is in the air. And if the breakdown strength of air when measured with AC power frequency and positive polarity switching wave shape are almost equal and of the minimum order. So wherever the breakdown strength of air is minimum, that determines the required clearance. Wherever it is more, the it is good enough. So as you can see it here, when I have tried, for example, 1000 kV peak. 1000 kV peak is giving you almost here, uh, 1000 kV peak is giving you almost here. Yeah, 1000 kV peak is giving you cutting, and this is the one. That means clearance requirement is of the order of 5 meters. For 1000 kV peak voltage, ACP power frequency peak voltage, the clearance requirement is of the order of uh, 5 meters, that is 500 centimeters. So is recommended by 500 centimeters. That means for each kV, how many centimeters? For 1500, for each kV, uh, half a centimeter is the requirement, isn't it? For each kV, half a centimeter clearance is requirement. That you can make a kind of a thumb rule. The clearance requirement in air with the other objects uh, is of the order of uh, um, uh, half a centimeter for uh, each for per kV, half a centimeter per kV, considering the peak value of the AC power frequency. In other cases, it is the peak value. So this is what is 0.5 centimeter per kV peak. You can say the requirement is 0.5 kV per centimeter, and the sorry, I've written wrong. 0.5 centimeter. I'm saying centimeter, writing kV peak. So this is a thumb rule. For all types of voltages, if you keep a clearance of the order of 5 kV, 5 centimeter per kV peak. So this is recommended by the IEC. Two of my colleagues have published a book, Hauschild and Lemke, book published by Lemke. You can refer. It is there in the reference also. They recommend the minimum clearance this way. For say 100 kV transformer, that means power frequency transformer, they recommend the minimum clearance with this way. That is 1.2 into 100 kV peak value. That means 100 multiplied by root 2 upon 5. Now that works out to be 34 centimeters. With this estimation, it will work out to be 50 centimeters, mind it, for 100 kV. So there it works out to be even less. According to Hauschild and Lemke, the clearance requirement is lesser than as recommended by IEC. How do they conclude? They conclude that it is the factor 1.2 should be taken uh, for uh, for the clearance requirement with the peak value, And five, the five uh, comes here as 5 kV per centimeter. 5 kV centimeter, if you remember, whenever there is a streamer breakdown or a streamer corona taking place in atmospheric air, what is the potential gradient, average potential gradient across the streamer in air? That is, we have talked about 4.5, or in round figure, you can say 5 kV per centimeter. So that has been taken to be the for clearance. In case at the maximum voltage of the equipment, that voltage is generated by the equipment, and 1.2 is the safety factor applied there, and that makes out to be 1.2 into 100 multiplied by root 2 divided by 5, and that works out to be 34. This is little more stringent uh, calculation. So I would say, with my experience in life, 0.5 centimeter per kVp is a very nice and very good clearance requirement. So I'll just show you uh, for grounding. The electromagnetic shielding is an electromagnetic shielding is provided in the laboratories. The whole floor is laid with iron mesh, and there are places where it is grounded, the mesh is grounded, and a ground or earth system is established in the laboratory in order to obtain a stable reference potential, which should be zero, supposed to be zero, but in case it may acquire some voltage, it is not desirable, so it is grounded, and which should be zero potential under normal conditions. It may acquire under some, when the current is flowing through the ground, it may acquire temporarily some voltage. You can imagine that. So all high voltage laboratories are provided on their floor, below the finish, a an iron grid which is grounded at specific locations. An earth metal grid, as you can see, embedded in the laboratory floor, is installed with the ground point readily available at suitable locations. So this is a provision. A grid under the floor is an iron rod mesh, and it is connected to the identified common ground point by large size copper conductors to the, as shown. So the grounding of the floor or grounding of the laboratory is also very important for safety purpose and getting the, yeah. So these are the aspects which are important when you set up a lab. I'll give you so that you have it here. These are the high voltage laboratories in India. As I was mentioning, the high voltage laboratory at uh, uh, at ISC Bangalore, and CPRI. CPRI, as you can see here, is also having a very good high voltage lab. Uh, CPRI Hyderabad, I have shown you. Uh, CPRI Hyderabad is the biggest. Then open air, or they have indoor also. But then you have BHEL Bhopal has got very big. Then CPRI Bangalore has very big. Then the Indian Institute of Science has got a very big lab, and uh, yeah, these are the biggest labs in our country. Then the next one, this is a list of high voltage laboratories in the world. As you can see here, in Germany, a very big high voltage laboratories, indoor, outdoor, are there. I've been talking about in France, then in Italy, in Canada, and in Japan and in UK, very high voltage laboratories are there. Even in Sweden and Brazil, very high voltage level. I mean, these are the as you can see here, there is no mention about USA. In USA, very high voltage laboratories are not there. Instead, in Canada, they are there. So, in fact, USA is lagging behind in the research for in the field of high voltage, and that is why they are more dependent upon the other countries in the world on high voltage experimental work or high voltage installations, etc. So I have tried to convey you little. I've taken a little extra time today to be able to convey all the uh, uh, possible things, and then you can keep it if you want. There are 10 experimental setups which are there in our book. You can refer from the book. These are experimental setup which we did set in the high voltage laboratory of IIT Kanpur, which the students can perform. This is the list of the experiments. So thank you very much. Uh, uh, I may, uh, I hope I will be able to take 2 hours more and try to give some practice of numerical examples, which also we have worked out in our book, so that some numerical example calculation practice reaches you to be able to understand the high voltage phenomenon in a better way. I thank you very much for your attention, and I hope you have learned something through this course. Okay, all the best.